Recording. Boom, there it is. Okay, I believe we're sharing, right? We should be sharing. You guys should see this. That's good. Okay, so where we left off was right ahead of this last few slides about Dash. So we just covered Quick, right, which is a sort of a hybrid of UDP and TCP. The next thing we're going to cover is Dash. Dash is basically a scheme for how YouTube provides connection appropriate video quality. So it's one way that YouTube deals with the quality of service problem. So YouTube, many other organizations use the Dash protocol for streaming video. So the basic problem is this: network conditions can change suddenly, right? You can be in one room of your house and have a great connection because you're right next to the router. You walk to another room, the router is suddenly behind a couple of walls, the connection isn't that great, and boom, right, your data rate collapses. So this can happen when that happens, when you go from a good connection to a bad connection, then your video player buffer can be very quickly overwhelmed by too much data, right? And what happens is if you have a great connection, YouTube says, oh, great connection, boom, I'm going to sign you up for the highest level of video quality, which naturally is going to take more data than a lower quality version. But you move to a lower quality, then what happens? If it still tries to force feed you that much high quality data, it's going to take a really long time, and eventually your video will get hung up while it waits for, more data to roll in so it can keep on playing the video. So the solution to this is essentially to allow dynamic selection of video quality during the process of watching the video. Basically, if you have a good connection, then it's going to show you high quality video segments. If you have a crap connection, it's going to show you bottom of the barrel video quality. And ideally, this sort of change happens at short intervals. So the data rate can be quickly adapted to any changes in connection capacity. So for example, if you move from a bad connection zone to a good connection zone, YouTube wants to quickly update that and give you high quality once again. So what's the mechanism for how it works? Well, core thing to keep in mind, higher video quality, whether it's in terms of more frames per second or higher resolution, whatever, it requires more data to be transferred. So the essential process for Dash, let's put it in Paint. We'll come back to the slides, but we'll put it in Paint because it's easy to understand. Imagine, first of all, YouTube has a video stored in highest quality, okay? It also stores that video in lower quality versions, okay? So a very simple idea there. So, and all of these video copies are pre-segmented into fairly identical chunks. Okay, for each quality type, for each quality level. So that is basically high quality video chunks are going to be about the same, low quality video chunks are going to be about the same. You get the idea. Okay, so what happens, suppose you're walking along. We're going to make a graph, and we're going to make it time versus connection quality, which leads to, equivalent to data rate. As the connection quality is better, the system can send you more data per unit time. So initially, what happens? You have, you have a good quality connection, and goes something like that. As you're walking along, suddenly it kind of drops off a cliff. You have terrible connection, and it goes back up for a while, but slower, and eventually resumes, right? Eventually you get good quality again. However it happens, this is the connection quality that you see. So the way YouTube deals with this, the way YouTube responds, it looks at your connection quality and how big the chunks are of the video and how much room you have in your buffer. Okay, because the big thing, the big concern is to keep the video playing smoothly, right? Basically, continuous play is more important than video image quality. Okay, so that's YouTube's perspective on this. So what happens, imagine if you have several different quality sizes, right? So you might have highest, high, medium, lowest. And how much data are these going to each take? Well, your lowest is going to be the smallest one, right? It's going to be a very small chunk of data. Low is not going to be much bigger. Medium is going to be bigger. High is going to be bigger still. And highest is going to be the most data. Okay? So I'll mark this as video segment data size. Okay. So what happens, initially, your video quality, and it sends you one of these, right? One segment sent, say, every 10 seconds. Okay. So initially, your connection is fine. It's good even. It's great. And so what YouTube sends you is this. Sends you the highest quality connection, right? It's the highest quality segment. As it's time to get the next segment, YouTube looks at your connection and says, well, it's still great. The buffer's still fine. Boom, we're going to send you another one, right? But what happens then? The next time it's ready to send you a segment, oh, it's dropped off a cliff. So maybe YouTube is going to send you, maybe your buffer's still good. It sends you a medium-sized segment. Okay. If I can pull this over, oh, maybe I can't. Try that once more. Come on, you. No, it just does not want to go today. All right, we'll do it that way. You saw it there. Grr. It's really hard to grab these things sometimes. All right, we'll do the big one. Boom. All right, so YouTube's going to say, oh, we'll send you a medium-sized one for this time. Then when the time comes to send you another one, the connection is terrible. So what does it do? Well, of course, it sends you the terrible quality segment, right? So it looks like that. And yeah, the quality is not going to be great at that point, but that's what there is. Now when it gets here, right, it sees, oh, a little bit of an uptick. So fine, that's what you'll get. Okay. And sends you a little bit better segment next time around because these things are coming around. When it comes time to send you the next one, it says, oh, okay, now it looks like you can handle a medium one. We'll do that. Whoop. Okay, we'll send you a medium one. We get up here, YouTube's like, okay, getting better. We'll send you a high one. And then eventually we get back up here and the time comes, YouTube says, ah, you can handle this. We're going to send you the whole big chunk. Okay, and it's back to normal. So this is basically the way Dash does it. Now, if you sit with the video long enough, if you keep the browser watching the video long enough after watching the whole thing, YouTube can start replacing lower quality segments with higher quality ones, right? Because it's going to store that information in your browser. It's cached in there, so it doesn't have to download everything again. But if you keep watching the video and your connection is good, eventually you'll see that YouTube will go back and start, oh, yeah, some of these segments here, well, yeah, if you're still watching it, then I'll reload these, right? So example, if you go back to here where the connection is good, or in here in the middle, YouTube's going to look at that and say, oh, here's a low quality segment, but you know what? Maybe your connection is really good now, so it's going to bring in the high quality ones. Okay, and that's basically Dash. And again, the point is connection quality can vary. When it does vary, YouTube wants to send you an appropriately sized video segment. Not in terms of length, but in terms of the amount of data that is involved in that video segment chunk. Okay. So a basic process here, video files get broken into short segments, each segment encoded to multiple degrees of quality. Whenever you're watching the video and it comes time to get a new segment, the video player checks the connection speed, checks the buffer state, and then the video player will select the highest quality version that can download without rebuffering. So basically, the best quality segment it can get that isn't going to really cut into the buffer. Okay, that's it. So that's Dash. That's about all there is to say about that. The other few slides here, we just got a few, right? We'll talk about open source and server architecture and some details, right? But not much here. Okay. So first thing, open source versus closed source software. So Dash is an open source system. What that means is the source code is made available to the public. Okay, so software development basically has two flavors, public or private. If it's private, it's called closed source or proprietary, meaning, somebody owns it. In private development, the software gets owned by the company that develops it, and it can only be modified as far as the developer permits. For example, Microsoft Office, right, has Excel. You can't go in and dig into the source code of Excel and change how Excel fundamentally works, but Microsoft will let you design plugins to work alongside Excel. So, and if you take some of the statistics classes or data mining classes, you might use some of that. And the way that the business generally makes money is either by selling copies of it or by selling licenses to use it. For example, UIC doesn't go out to Best Buy and buy 1,000 boxes of Microsoft Office. It buys a license that allows, however many people to use it within its organization. Okay. The public model is open source. In that case, the software isn't really owned by anyone. The source code is made public for anybody who wants to use it. It can be developed or modified by anyone. Okay, so in the case, for example, there's an open source operating system called Linux. And in principle, anybody can show up and try to add some new module, new feature, and provide code for that. And if it's good, the people who govern Linux will implement that in. So it's sort of like Wikipedia for code. Anybody can show up and join, but there is a little bit of an evaluation process before your updates get included. Now, the revenue model for this, number one, typically by providing training and tech support. But in many cases, there is no revenue because it's not owned by anyone. The typical usage license is that it's the base code was provided free to you, so you can't add on to that and then try to sell that as a product. That's a standard usage license for open source software. Now, as far as security pros and cons, there is something to be said about this. There are people out there who are very strong open source code advocates. And if you had asked people about this 15 or 20 years ago, people would have maybe a lot of strong opinions saying, yeah, open source is the way of the future. It's how everything's going to go. People are going to be able to make enough money doing this. But obviously, we can look around and see there's still plenty of closed source code out there as well. So open source hasn't done away with the closed source model. There's still plenty of things out there that you got to pay to use. There is some truth to the idea that open source tends to have better security than closed source. So the idea with closed source, the good points about that is that the source code is not available to the public. Thus, it's harder for the bad guys to look inside the code and figure out all the flaws in it, all the vulnerabilities. The downside, of course, with closed source is that you inevitably have a smaller pool of people looking at it. They might be very good people, but they're human, and these are complex systems, and they're going to miss some stuff. And that's why, a lot of code out there comes with some kind of security vulnerabilities that eventually have to be patched over. With open source, in many cases, it does work better because you have a lot more people looking at it. Right? It's basically open to the whole world. So it's like saying, well, whatever flaws are there, people are going to find, but there are so many good people looking at it that there probably aren't going to be many flaws that make it through the design process. So again, it's not an absolute metaphysical certitude that open source software is going to be more secure than closed source, but it does tend to have a bit of advantage that way in practice. Okay, other things, quality of service, server system architecture. So just like Facebook and Google, YouTube is really big and it needs systems that are scalable to maintain quality of service, right? So for example, it has all these videos stored in multiple levels of quality, and you might have a situation where thousands or even millions of people want to watch the same video at the same time. It's potentially a big headache. And what we've seen actually in recent years is that there's been a tremendous jump in the last 5 years of mobile usage. So this is an article from 2015. They say people now spend an average of 40 minutes on YouTube per viewing session. So just up to a couple years before that, people had been mostly going to YouTube, watching maybe 1 or 2 videos and going away. Now YouTube, it tends to be something people create playlists, watch lists, they put them on, they just, you know, have it as background noise, sort of their own personal radio mix. People tend to have longer sessions on YouTube than they used to. Anyway, and that's remained pretty stable in the years since. But yeah, there was a big uptick over a stretch of a few years there. So anyway, it's a big system, and maintaining quality of service is difficult in big systems. So the basic principles, number one, as far as it can do it, handle all requests locally. So videos that are locally popular get cached near their demand sources. For example, if you have some Finnish language news segment that's uploaded to YouTube, unless there's a really good reason for people around the world to watch it, well, it's in the language of Finland, which is a tiny country and about the only place in the world where anybody speaks Finnish. And so, yeah, you're going to put it in, you know, whatever kind of data center you have up around there. Maybe they have one in Helsinki these days. I don't know. Other things, track trends upward and downward. So when videos are becoming more popular, it's going to do things like replicate them within a data center, possibly replicate them to other data centers so that multiple people can watch them at the same time. It can have multiple connections that way. And same thing for downward. As videos become less popular, they're going to get shuffled out of the mix. And again, this is a way of prioritizing which videos are more accessible. So if you have a video that's being watched by 1 million people simultaneously, well, you probably want to store that in RAM if you can. Other things, predicting requirements, monitoring usage, providing backup capacity against failures. These are all the standard things that these big scalable systems do. They try to predict over time how many servers they're going to need available to meet the expected level of demand. They're going to track whether the predicted level of demand actually materializes, and they're going to have a certain amount of backup capacity so that you don't go to YouTube, start a video, and something goes wrong and it crashes and you can't recover from that. Okay, but of course you're watching videos, so this is much easier to do. There's not a whole lot of upstream traffic going from us to YouTube. It's basically pick which video you want, which is a tiny packet that gets sent out, and then YouTube is going to send you like a gig worth of video stream data. Okay. Now, similarities with Facebook. So remember when we were talking about Facebook's photo management system, photos are typically uploaded once, viewed many times, very rarely deleted, right? So when you upload a photo to Facebook, it's basically a static piece of data. You're not going to go in there and edit it really on Facebook. And also, photos get grouped in albums and retrieved in batches for faster delivery, right? That was one of the things that Facebook implemented with Haystack. Well, these same principles apply to YouTube, right? Videos generally uploaded once, hopefully viewed many times, right? I just saw a list that they had like hundreds of videos now that have been viewed more than 1 billion times. And of course, videos are very rarely deleted. Now, a video file is essentially a sequence of images with an attached audio stream. So retrieving a video is actually a lot like retrieving a very big photo album. But the one benefit is videos are more easily compressed than a set of unrelated images. We'll talk this isn't a video compression course, but I'll talk briefly about why that is. So imagine if you have some opening credit screen on a movie, right? Opening credits, right? So what's the movie called? I don't know. Movie. Part 2. Okay, and down at the bottom it might say something like, yeah, that's not what I want. Down at the bottom it might say something like, starring Joe Blow and sure, Susie Slacker, I don't know, Susie Sunshine. Okay, and this bit of screen is going to sit here. The screen might be static for 10 seconds or so. Well, if your frame rate is 32 per second, 32 FPS, then that's 320 frames. So instead of sending the same frame 320 separate times, instead the compression software will send frame number one, and then plus, a times 319 for the rest of the sequence. It'll basically say, okay, here's frame number one, and for the next 319 frames, just repeat this scene. And there are other times that can happen actually within the screen itself, right? So again, different kinds of video compression software. Imagine if you have a scene inside a car, right? So you're viewing it from inside the car, and as the car is moving along, all this stuff on the outside is going to change, right? So maybe there's like, trees by the side of the road or something, I don't know, and there's a road in the middle. We'll just, well, I'm drawing some trees here, right? You get the idea. There are trees and more trees, and as you're traveling along, sure, the trees change. They're going to move relative to each other, but what isn't going to move is the rest of the stuff in the car, right? So this part here, this inside the windshield, this is the only stuff that needs to change on the video. And there'll be some polygon that says, frame one, bring the whole thing. Next, X frames, just update the area inside the polygon, right? So they'll say the only thing that's going to change is stuff inside this area. And then I'm just going to do it with pencil. And then everything else on the outside, you don't have to send data for this. So anyway, key takeaway, video compression generally tends to be more effective than unrelated image compression, for the reasons that we've just discussed. Okay, now last little bit on this, reverse engineering. So YouTube has been kind of a secretive organization. It's hard to find a lot of details about how they work or how much revenue they're making, but we do know a few things. Number one, YouTube has a bunch of different server tiers to cover its global operations. So basically a bunch of different data centers, and videos are, as far as possible, locally cached where they're popular. Okay, and again, for all the same fundamental reasons as Facebook, as far as faster response time and providing backup against failures, right? If one data center goes down, some of the other ones can take on the load, things like that. Now, these details, were basically broadly known as far as the big picture. Yeah, YouTube has different facilities in different locations, but there was a wave of people around 2011 that were reverse engineering YouTube's data streams to see where it came from. So for example, if this PDF is still up there, let's see. This is an old conference paper, Dissecting Video Server Selection Strategies in the YouTube Content Delivery Network, CDN. I didn't like something there. There we go. Okay, so this, if you go down and read through the whole thing, right, you don't have to, you can just read through this. The short version is one of the big reasons, the way that they could basically pick apart the way that YouTube selected where it was going to copy a video from. So a lot of it was about geography and language. Those were the big things. If, for example, like I said, if the video is in Finnish, then it's probably going to be stored in a data center near Finland. Okay, if you're really motivated, you can read through that, but it's not cooperating too well with the browser and the PowerPoint slides at the moment, so I'm gonna let that go. Okay, and that's what I have to say about, yeah, see, some shit's just crashing there hard. Okay. Okay, so that's what I have to say about this particular lecture. If there are any questions, we will resume them in the next one. Okay, so I'm gonna go start up the other session.